CD is for compact disc. It does not stand for cookie dough. Okay, so when a compact disc or a CD is played, what's actually happening on the inside of it is sometimes the way they work is the angular velocity of that disc, or how quickly it's rotating, is such that the linear or the tangential speed of the area being read by the player is held constant. So if you only want to read so much linear speed at a time, if you're reading the outer edge of the disc, it's going to spin, the disc itself is going to spin slowly, because we know that outer disc is going to spin faster linearly than the inside. And if you're trying to read the inside of the disc, it's going to spin fast, because we know linearly that's moving slow. And that's why your CD changes speed as you listen to it. So if we know that the angular velocity can change, but the linear, the tangential velocity is staying constant, then how can we figure out the following? If we know that the angular velocity, omega, of the CD, when the player is reading at a distance of 3 centimeters from the center, is 3.51 revolutions per second. What's the angular velocity when the player is reading at a distance of 4 centimeters from the center? Okay, that's a lot to take in, so let's just doodle a picture here, okay? Here's a CD. This center right here is the axis of rotation. That's where you snap your CD in and then it starts spinning around, okay? We know that when this CD is 3 centimeters out, right here, we know that its angular velocity, omega, is 3.51 revolutions per second, which, let's be honest, that is not a kind unit. That is not a kind unit at all. I want radians per second, not revolutions per second. So I'm going to have to do a conversion there. On the flip side, so we've started to read a different part of the CD. We're still rotating around the center, but this time we're not at 3 centimeters out. We are at 4 centimeters out. So we know since we've moved farther out on the CD to where the disc would be moving faster linearly, we know that this omega has to change. And hopefully, and in theory, this omega should go down. Because if I want to keep the linear speed the same, then if I moved fast, where naturally the linear speed would increase, if I just slow the disc down, then that increase and decrease will cancel out, and I'll keep constant. So let's try to work this out. The first thing we can do is just figure out what is the linear speed that this disc is spinning at. What is the linear speed the disc wants to be reading? And the way we do that is say V equals omega times R. Now, there are some caveats to this omega times R, because our R value here, which we have as 3 centimeters, well, that's going to be written as 0.03 meters. We simply divide 3 by 100 to get that into meters. Now, the 3.51 revolutions per second, we need to do a little bit of a train track on it. We already have per seconds, but to get rid of the revolutions, we multiply by 2 pi radian per 1 revolution. This dumps the revolutions, and now we have radians per second. When we do this, we want to make sure that we multiply by both the 2 and the pi, because when we do that, it'll make it a little easier down here, because we want this velocity to not be in terms of pi anyways. We want it to just be some number. So if we take 3.51 times 2, that gives us 7.02, and then multiply by pi, that gives us 22 and a little bit, but we're just going to say it's 22 radian per second. Multiplying 22 times 0.03, that gives us a linear velocity, or a tangential velocity, of just 0.66 meters per second. The radian goes away here. Radian meters are not a thing. So this is the linear velocity that the disc wants to hold at. So as it moves further out on that disc, the angular velocity has to go down to maintain this quantity. So if we go to the other side here, we're going to have the same equation. The linear velocity equals the angular velocity multiplied by the radius, or the radial distance you are away from that axis. In this case, we want to keep that linear or tangential velocity the exact same. So we'll bring our 0.66, which we just found, and we'll tuck it in. We also happen to know what the new r value, that new radial distance value is. It's 4 centimeters, or 0.04. So when we write this over here, we're going to have 0.66 meters per second equals omega times 0.04 meters. To solve this is fairly straightforward. We divide each side by 0.04 meters. When we do that, we see the meters are actually going to divide out. So at the moment, we just have units of 1 over seconds, which equal omega. And 0.66 divided by 0.04 is going to give us a value of 16.5. Now, an interesting thing here, even though these units are 1 over seconds, it's important for us to remember that what we're really talking about here are an amount of angle that you're going through, which means instead of this being 1 over seconds, it's really implied that this is stating radians per seconds. And that is how our new angular velocity should be whenever we move further out on that disk. Now, you might be looking at that and saying, hey, 16.5, that's greater than the 3.51 we had in the beginning. Did we mess up? You said it was going to slow down. No, we didn't mess up. Recall, this is in radians per second of 16.5. The radian per second value we solved for was 22. So indeed, whenever we moved further out on that disk where things were rotating faster, we slowed down our angular rotation, our angular velocity to 16.5, and that kept the linear velocity constant at 0.66. So now, that you know how your CDs players are kind of working, maybe you can use them more often. Or maybe it's the year 2042 and we don't use CDs anymore. We use embedded microchips. But until then, adios and take it easy.